Hi, it's Mrs. V here. It's time for part 3 of our series on how you answer test and exam questions that involve equilibrium changes and Le Chatelier's principle. Today we're going to talk about temperature changes. Let's get our whiteboard on and get straight into it. You'll remember our 4-part recipe for Le Chatelier success. We're going to follow those same steps today. So let's apply those to temperature changes. Temperature changes, exothermic, endothermic reactions. Some things to remember. Exothermic reactions produce heat. Endothermic reactions use up heat. Exothermic reactions have negative delta H values. Endothermic have positive delta H values. Just a little reminder. First example, A plus B in equilibrium with C. Our delta H value for this reaction is negative 217 kilojoules per mole. What type of reaction is that? That's an exothermic reaction. And the way I like to think about reactions in Le Chatelier problems is to think of heat as a reactant or product. So for an exothermic reaction, I like to think of heat being a product of the reaction. So A plus B makes C plus heat. And that makes it much easier to think about which way the position of equilibrium will shift. So we're going to look at what the effect is of increasing the temperature. So why is the system no longer at equilibrium? Well, Q hasn't done anything, but Kc, the equilibrium constant, is different if the temperature changes. So the reason that the system is no longer at equilibrium is Q doesn't equal Kc, but that's not because Q changed, that's because Kc changed. So all you have to do here is say that Q does not equal Kc anymore because Kc is different at the new temperature. Now, according to Le Chatelier, let's work out what's happened. We are increasing the temperature. So increasing the temperature, I like to think of that as adding heat. And if I add heat, then I'm going to want to counteract that by using up heat. So I'm going to have to take the reaction back over to the left because that is going to use up the heat. What does that mean when equilibrium is re-established? Well, A and B will have increased because the position of equilibrium is moving over toward the left, and therefore C will decrease. But the tricky part of a temperature change is what happened to Kc. So let's have a look. Kc is concentration of C over concentration of A, concentration of B. What did we do? This one's now smaller. This one's bigger. And that one's bigger. So you're going to end up with a smaller number and you're dividing it by a bigger number, which means Kc is going to decrease. Of course, we are going to show all of this on a concentration time graph. So here we see A, B, and C all at equilibrium. We know they're at equilibrium because the graph is horizontal. What happened then? We changed the temperature. What did that do immediately to their concentrations? Absolutely nothing. So there's no immediate change, no vertical part on the concentration time graph for a temperature change. What did we see happen? We saw that A and B increased, and C decreased. Bring them all back to equilibrium. Nice flat graph, all happening at the same time. That one's terrible. I'm doing that one again. And of course, 1-to-1 mole ratios. So no vertical part on the graph. That's an easy way to recognize a temperature change on a concentration time graph. Let's look at our Haber process. We're looking at some actual data now. Nitrogen and hydrogen in equilibrium with ammonia. Delta H is minus 92 kilojoules per mole. What kind of reaction? Exothermic. Negative delta H. So that means I'm going to have heat here as a product of the reaction. What's the effect of increasing temperature? We're going to think of that as adding heat. The temperature change, remember, it causes Kc to change. So Q is not equal to Kc anymore, and the system's no longer at equilibrium. According to Le Chatelier, what will happen? Well, if we want to be using up some of that extra heat, we're going to need to go away from the heat on the reaction. We're going to need to go over to the left. How does that counteract the temperature change? It uses heat. And when equilibrium is re-established, nitrogen and hydrogen will have increased and ammonia will have decreased. What will that do to the value of Kc? Kc is the concentration of ammonia squared over the concentration of nitrogen, concentration of hydrogen cubed. So we've got a smaller number on the top, and we've got two bigger numbers on the bottom. So smaller over bigger is going to be a decrease. Concentration time graph, we're getting quite good at these by now. Remember, a temperature change has no vertical part of the graph. So just all of a sudden, everything goes into its reaction rate curve. We need to have a mole ratio operating here. So nitrogen and hydrogen both increased and ammonia decreased. So nitrogen will have a mole ratio of a relative change of 1. Hydrogen, a relative change of 3. And ammonia, remember ammonia is on the other side of the equation. It needs to go down if the other two have gone up. Now they're all back at equilibrium. I'm going to just draw that flat line again. I'm really not good at the bottom one. There we go. And if you weren't on graph paper, you would say that was X, that was 3X, and that was 2X. That's just about a wrap for how to answer Le Chatelier questions in tests and exams. Hope you enjoyed the video, and I will see you in the next video.